There's a telling time category. That's a tough one. All right, so we're not going to really sweat the first three. Number one, in case you're curious, that's inductive reasoning. She's just kind of being funny. Number two, Jeremiah gets extra credit because he wrote a nice half paragraph about, I don't know what it was because I haven't read it yet, but I'm looking forward to it. But mostly we were just looking for the definition of inductive reasoning. So looking for patterns, making conjectures. Okay? And then number three is on is what is deductive reasoning. And deductive reasoning is about using a sort of step-by-step logical argument to prove that something is true. Okay? So those are the main things going on there. All right, number four. Next two numbers are 19 and negative 30. That was a strange one. It's the Fibonacci sequence backwards. Instead of adding the two previous numbers together, you subtract them. So 7 minus 2 is 5. 2 minus 5 is negative 3. 5 minus negative 3 is 8. Negative 3 minus 8 is negative 11. And then to get the next one, you go 8 minus negative 11, which would give you 19. And then you go negative 11 minus 19, which gives you negative 30. Okay? Number five, it's a 2-for-1 pattern. You've got a letter pattern and a number pattern. The letters are skipping one more each time. So to get from A to D, you skip 2 letters, B and C. To get from D to H, you skip 3 letters, E, F, and G. And to get from H to M, you skip 4 letters, I, J, K, and L. So to get to the next one, you would skip 5 letters. So N, O, P, Q, R. And then the next letter is S. And then 4, 9, 16, and 25, they do have a pattern because it's going up by 5, then by 7, then by, going up by 5, then 9, then 11. But those numbers are special numbers that you should learn to recognize and love. What are those numbers, McGuire? Those are the square numbers. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and so the next number would be 6 squared or 36. All right, number 6, they give you a little formula, and then you have to come up with the first 6 numbers in the series. And the way you get the first one is you plug in 1. So when I plug in 1 there, 1 squared is 1 plus 1 is 2. Then to get the second number, you plug in 2. So if I plug in 2, 2 squared is 4 plus 1 is 5. To get the third number, you plug in 3. 3 squared is 9 plus 1 is 10. And now you should see there's a little pattern going here. This is plus 3. That's plus 5. So the next one's going to be plus 7, which is 17. Then we're going to go plus 9, 26. And then we'll round it out by plus 11, 37. So you can get those numbers either by using the formula that was given, or you can just get a few of them and then use those to find the rest. Same dealio with number 7. It's 2 to the n minus 1. If you plug in 1 for n, 1 minus 1 is 0, and 2 to the 0 power is 1. That's a hard one to remember, but any number to the 0 power is going to be 1. Okay? Now if you plug in 2, 2 minus 1 is 1, and 2 to the first power is 2. Let's get one more and then we'll be able to see the pattern. Now if you plug in 3, 3 minus 1 is 2, 2 squared is 4, and so they're getting doubled each time. Now this is one where you'd have to be careful, because you might look at this and go, okay, this is up 1, this is up 2, so the next one's going to be up 3. But that's incorrect, because if you plug in 4 here to get the fourth term, 4 minus 1 is 3, and 2 to the third is 8. And so they're actually doubling every time instead of going up by 1 more. And so that's why inductive reasoning can be dangerous, because it can lead you down the path to evil. Yes, the path of wrong answers. All right, are those okay? Okay, number 8, I'll put the answer up here.
Easy.
And just remember, I'm not an art teacher. Wait, I didn't have to remind you that I'm not an art teacher. It's obvious. I'm looking at my art.
Oh, it looks beautiful.
What did you say? It looks beautiful?
Yeah, I said it looks beautiful.
All right, so the thing on the top, that shaded rectangle on the top, was moving around the top of it counterclockwise. This little shaded rectangle on the side was moving diagonally, so it started here, then it went down, then it went up, and so now it would be down again. And then these two shapes were also rotating around. I think they were actually going clockwise, and the triangle was bouncing between shaded and unshaded, and so this one would be shaded. Okay? All right, number 9, they showed an unfolded triangular base pyramid, and then they showed a constructed square base pyramid, and then they showed an unfolded pentagonal base pyramid, and then they showed a constructed hexagonal pyramid. So what's happening to the base of the pyramid each time?
It's going up by 2.
Going up by solamente uno, mi amigo, just 1. 1, 2, 3, 4, 5, 6, 7. So the next one should have 7 sides. And then it's also alternating between unfolded and folded up. And so this one would be of the unfolded variety. So it looks something like that. Okay? All right? Ask Mr. Aldridge.
Doesn't Curtis have the black mark on today?
He does, yes. Right here. Oh, that reminds me of a joke. 10, we are supposed to figure out the sum of the first 30 odd numbers to start with. And so what you supposedly have learned so far in this chapter is to solve problems like that, you always look at a simpler case, right? So we're going to break this down and look at the sum of the first 1, and then 2, and then 3, and see if we can come up with a pattern. So this was the odd numbers, right? First. Okay, so if I add up the first odd number, what do I get? 1. If I add up the first 2 odd numbers, I get 4. If I add up the first 3, I get 9. And if I add up the first 4, I get 16. Okay, so what's the pattern?
3, 5, 7. Odd numbers.
Multiplying it by itself each time. These are our square numbers. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So my formula would be n squared. So if I wanted to add up all 30 of them, instead of taking the time to add all those up, 30 squared is 900. Okay? So that's how that works out. Okay, the next one, doing the same thing with the odd numbers, was quite a bit trickier. And there is only one of these problems on the test. I mean the even numbers, sorry, thank you. There was only... Oh yeah, because I told you guys to skip it because my 4th grade class figured out it was really hard.
It was easy. It was 9:30.
All right.
There's one more of these.
Did we skip 13 also?
Yeah.
Okay, sweet. All right, number 12. No, I feel bad though because you guys are kind of missing out on the phone. You didn't say the joke.
I don't know how.
Okay, so number 12, here we go. These are ones, McGuire, Jacob, because we were gone, the whole end thing, so here it is. So whoop, dial in. Perfect, stay there, stay right there. All right, this is an easy one because what is it going by every time? It's going down by 3 every single time. And when the pattern is exactly the same, coming up with the formula is easy. Since it's going down by 3 each time, what do I write? Negative 3n. And then I have to figure out what do I need to do, what do I need to add or subtract. It's always going to be either adding or subtracting to this to get this, okay? So if I plug in 1 for n, that's negative 3. But I want my answer to be 2. So what can I do to the negative 3 to get 2? Plus 5. And so that is the formula for that table. Negative 3n plus 5. Okay? So now that I know that, I can figure out what it's going to be for 20 by just plugging it in. Negative 3 times 20 plus 5 is negative 60 plus 5 is negative 55. All right? So those should be pretty easy when it's going up or down by the same amount every time. When it goes up or down by is what goes in front of the n. And then you need to figure out what you add or subtract to that to make it work. Yes, I will. I'll give you a number of examples. For example, I'll give you an example of Victoria, the store window designer, who's going to make a tower of blocks 30 feet tall, or 30 blocks tall. She wants to figure out how many blocks she would need to be able to do that. Okay? And so what we're going to do with this is we're going to look at how many blocks it would take if she made everything 1 block tall. 1 block. Okay. Then she says, well, what about if I made it 2 blocks tall? What does that look like? How many blocks? 4. Then 3 blocks tall. Oh, did I screw that up?
Yes, you did.
No. Like that?
Yeah.
Okay. How many blocks do I have there? 9. Okay. Do you see the pattern?
Square.
You should see the pattern.
They're all squares.
It's squaring. That's the 3rd time we've seen a squared one. So 4 blocks high would be 16, because 4 squared is 16. So the pattern is n squared. And just like if we added up the first 30 odd numbers, if I want to make a 30 block tall tower, I would need 900 blocks. Okay? A lot of blocks. It is not as many, however,
5,000.
as I would need, that's right, for the next one, which is where she's going to make a little different kind of tower. And this time it's going to be 100 bricks high. So level 1, 1 brick, 1 brick. 2 bricks tall, 3 bricks tall. 3 bricks tall, 6 bricks. Okay? And it went up by 2, then up by 3, so now you're guessing it's up by 4. Okay, so the next one would be 10. Okay, so now we need to come up with a formula for that.
No. Yeah, it would. No, not how you run bowling.
Oh, good call. Yeah, bowling, 10 pins makes a little pyramid. Okay, yeah, exactly the same thing. All right, do you recognize these numbers? The 1, 3, 6, 10, okay? These are, like you said, are triangular numbers because the bowling pins are in a triangle. You ever do the Wii Sports and you can do like 100 on the base?
I got all of them.
Awesome, and it has the walls on there. All right, so the difference between these numbers and the handshake numbers, the reason why we can't use the n times n minus 1 over 2 formula is because the handshake numbers, if you have 1 person in the room, then you have, right, 0 handshakes. So they're the same numbers, but they're shifted a little bit, okay? So we're going to have to do a little thinking to figure this out. So if we think of these instead of being bricks, think of them as what we've used before, handshakes. How many people would there have to be in the room for us to get one handshake?
2.
2. How many people would have to be in the room for us to get 3 handshakes? 3. And how many people would have to be in the room for us to get 6?
10.
4 handshakes. Okay? So if I draw that out, if I make a little geometric model out of that, now I can make the other table. How many line segments are coming out of each point here? 1. How many are coming out of each point here? 2 from there, 2 from there, and 2 from there. How many are coming out of each point right here? 3. So these numbers are also going up by 1. Okay? So if these numbers on top, here we go, this is what it's all about. If these numbers here on top, 1, 2, 3, 4, are the ends, what are these numbers down here? N plus 1. All of these are 1 bigger than the ones above. Okay? What are these numbers right here? N. And then here's the trick that we've used so many times. Hold on a second, Sarah. What do I do with these two things to get these numbers here? Multiply them and divide by 2. Okay? And Sarah's about to tell me that I totally screwed up. Yes. This is number 15. Yeah. Yeah, stack of bricks, 4 bricks high. So I know it's confusing because 16 is about handshakes, but we're just using the handshake idea to solve this problem. Okay? So you should have 2 different things in your notes. Okay? 0, 1, 3, 6, 10. That's the handshakes. And that is n times n minus 1 divided by 2. All right? We're taking a break. 1, 3, 6, 10, 15. That's the, technically the triangular numbers, and that's n times n plus 1 divided by 2. So they're really the same sequence, but they are, one of them starts at 0 and one of them starts at 1, and so the formula is just a hair bit different, okay? And so those of you, bless you, that have been struggling to come up with these formulas, if you have those in your notes, then that means you have to spend less time coming up with the formulas yourself. You just have to figure out which problem matches what formula. Okay? It is. It's crazy. But it just might work. Yes, because we're running out of time. All right, so now I can use this to figure out how many bricks I would need to make a 100 brick tall stack. It would be 100 times 101 divided by 2, which comes out to be, somebody said before, 5,050 bricks. 10,100 divided by 2 is 5,000. Okay? All right, so now that we have those formulas, everything in our lives is simple. So the very next problem, number 16, like Sarah said, does deal with handshakes. It says there are a total of 741 handshakes. So which of these two formulas do I need? N minus 1 or N plus 1? N minus 1. So I'm going to take the number of handshakes and set it equal to N times N minus 1 divided by 2. Okay? How do I solve that?
Times it by 2.
Times both sides by 2. So that means 1482 equals N times N minus 1. I showed you the other day there is an algebra way to solve this.
That was their geometry.
I don't know that there's a geometry way to solve this one. We're going to just guess and check. Give me a guess.
35.
35. So if I go 35 times 34, do I get 1482? No, too small.
39.
39.
31. 31.
39 times 38, hey, what do you know, 1482. So since 39 times 38 equals 1482, there must have been 39 people at the party.
I hope you're thinking better. That doesn't make sense. Hey, you know what?
All right, so let's do number 17, because this kind of puts all of this together. If a whole bunch of lines, no two parallel and no three concurrent, intersect in a plane, 2,926 times, how many lines are there? So this is how easy these problems are now. One line, how many times does it intersect? Zero. Two lines, how many times? One. Okay. Three lines, how many times? Three. And just for funnies, four lines would be 1, 2, 3, 4, 5, 6. Okay? So, go back to the thing here. Are we handshakes or triangular numbers? Handshakes, because we started at 0. Okay? So we immediately know that our formula is n times n minus 1 divided by 2. This is one of the weird backwards ones, though. It says there were a total of 2,962 crossings. So just like in the last problem, I need to set that equal to n times n minus 1 divided by 2. First step is to what? Multiply by 2. So 2,962 times 2 equals. So I need two numbers that need to multiply together to be 5924. 77 times 76. What were we looking for? 5924? Nope, very close.
78.
Let's try 78 times 77. Whoa, what happened there? Jumped right over it.
It's supposed to be 26.
It's supposed to be what?
2,926 times.
It's supposed to be what?
2,926 times.
Oh, 2,926 times. Aha. Okay, so I did that wrong. The answer is 77. Okay? All right, and then the last one that I'm going to work through with you guys, and then we will give you your practice test to work on, just so there's no confusion. You don't always have to use that complicated formula. Now we are counting regions that are formed when we draw one diagonal, or no, I'm sorry, all the diagonals from one vertex. So if I have a triangle and I draw all the diagonals I can from this vertex over here, how many regions is my triangle divided up into? One. If I have a quadrilateral and I draw all the diagonals I can from one vertex, how many regions am I divided up into? Two. 1, 2. No, because I'm only drawing just from this diagonal. Okay? Now I'm going to take a pentagon and draw all the diagonals that I can from one vertex. How many regions do I get now? 3. And so your guess would be with 6, it would be 4. Okay? So these numbers are easy. They're all going up by 1. So I would say 1n, or just plain old n. And then, yeah, since they're all 2 less than the ones we started with, it's n minus 2, which means there are a total of, if I draw a 54-sided figure, 52 regions. Okay? What? Yeah, I know there's a few left, but I want to give you enough time to work on your practice test. So will you turn those in, please?